Hello and welcome to another video. In this one I'm going to use the integral test for analyzing the convergence of series. So first of all, do you remember improper integrals? You know, those integrals which were defined at infinity? Well, when we studied them, we had this method, right, where we used series to bound my improper integral, and we said, well, most of the time, this is not really going to be that exciting, not really that useful, but you know what's really going to be useful? To use improper integrals to bound series. So let's do that. Let's actually use improper integrals to bound series. So how do we do it? Let's actually use it for the proof that I've been owing you for a while, proving that this thing converges, that 1 over k squared converges. So how do I do it? Well, we're going to use improper integrals. So let's use the function 1 over x squared. And let's do the following improper integral. An improper integral from 1 to infinity of 1 over x squared. Now, we know it's decreasing. So if you go back to our method of bounding improper integrals using series, you know, those little boxes we were drawing, well, you will know that if it's decreasing, then it's going to be bigger than this thing here, right? Then from 2 to infinity, and smaller than from 1 to infinity. Okay? Go back if you don't remember this, stop the video now and go back to this video. It will be very helpful to see it. So this is what I'm using. I'm using that thing that I know about from improper integrals, right? So let's do it. So let's actually solve this integral because I know it. I know how to solve this integral. So I can solve it quite quickly. It's going to be minus 1 over x, and then once I define it, this thing, when I substitute with infinity here in the limit, it's going to give me 0, and I'm going to end up with minus 1, which becomes 1, positive 1. So that's what improper integral gives me. Now, of course, if I just substitute that in here, I'm going to just get a 1 here, right? Instead of this big chunk here, I'm just going to put a big 1. The problem with that is that all I'm getting is a lower bound. I'm just going to do 1 is smaller than the sum from 1 to infinity of 1 over k squared, right? Realize I put a 1 here. Okay, so this thing here is bigger than 1. But I'm studying this thing, not this thing. I'm studying from 1 to infinity, not from 2 to infinity. So just putting a 1 here is giving me a lower bound from 1 to infinity. But lower bound doesn't give me convergence. And that's what I'm studying. So how do I do it? Okay, well, here's the thing. I know that this is what I know from the left-hand side, right? I know that this thing here is smaller than 1, right? Great. But let's do the following. So what would be the first term here? What would be the term with k equals 1? Wouldn't it be 1, right? If k equals 1, I get 1 over 1 squared, which is 1. So if I put this thing here and I put it on the other side, well, the inequality remains. I'm just adding 1 on both sides. And 1 plus this is just going to be the summatory starting from 1, because I know that this is the first term. So I can include it in here just by changing the k equals 2 into k equals 1. And what do I get on this side here? I get 2. And that's how I get my upper bound. So now I have a lower bound, which is 1, and an upper bound, that's 2. That's great if we just bounded it. But what's most important for us, we've shown that it converges. So there you go. That's my proof using the improper integrals, using the integral test. So now, this exactly, what is it? What does it mean? Well, very quickly, in a much more, perhaps, easier way to handle it. This is simplified. This is rather than try to like keep bounding a series, it's just simplified to determine convergence. So if I have a decreasing function, f of x, where x is bigger or equal to 1, then if I do the integration and that integration in that improper integration to infinity converges, then the series also converge. And note how I've changed the x for the k. And if this one diverges, then so does the series. That's it. That's a simplification of my integral test. I can always use it to bound it, which is fantastic, which is great, which is wonderful. But in terms of convergence, which is really what I'm going to be caring about in this section, much easier. Just do the improper integral. Does it converge? Then the series converge. Does it diverge? Then the series diverge. End of the story. Nothing else to worry about. Very quick, but of course very quick if we know how to integrate that thing. Excellent. Let's just do a few examples. Oh, look at this one. Does this thing converge or diverge? Not that straightforward. But actually, if I look at this thing here, I might realize, well, if I make the derivative of this part here, don't I get this part here That reminds me a little bit about integration by substitution, perhaps. You know, like, hey, I was integrating this thing and I got this thing here. Isn't that where I do integration by substitution? Might not that thing work? Let's use it. Let's use that idea. So all I have to do is integrate this thing here. Now, to integrate it, how am I going to do it? Well, first let's do the indefinite integral. The reason why I do that is because since I'm going to do a substitution, I should technically be changing these limits. So let me first solve the indefinite integral. And once I've solved indefinite integral, then I'll put the spaces. It's just a matter of a good, let's say, mathematical grammar. Good way to write it and not write things that might be misinterpreted. Let's first do the indefinite integral, and then we'll go back and put our limits, our definite integral in. So again, as I said, I'm going to use substitution. So u is equal to 1 over x, du is going to be equal to minus 1 over x squared dx. I take this thing to the other side, and I get that dx is equal to minus x squared times du. I make the substitution, and this is what I end up with. And this minus x squared is going to cancel with this x squared. So I'm going to end up with this very easy integration, which comes out to be cosine of u. Great. And I now substitute the u back again to 1 over x, and there we go, I got it. That's my integration. Wonderful, beautiful. So my definite integral, which is this thing here, ends up being my definite integral from 1 to infinity of cosine of 1 over x. Once I do my substitutions, I'm going to end up with, again, the limit as x goes to infinity of 1 over x, and that's going to tend to 0, so it's going to be 1 minus cosine of 1, which means that my integral is convergent, because that thing is finite. So if my integral converges, then the series also converge by the integral test. There you go. That's a good application of the integral test. Now, here's a consequence of the integral test. It's called p-series, and it's a very useful thing. So you realize that we saw that this thing here converges, right? Now this thing, I can also write it as k to the power of minus 2, right? Okay, you agree, no? And we saw that this thing converges. Excellent. So for what values of p will the series of k to the power of p converge? Massively important question. Well, we can actually figure this out using the integral test. Let's make this like an important question. Let's figure this out. This is a part of your syllabus, okay? This is mentioned in your syllabus as something you have to know about p-series. It's not just a random example. Let's use the integral test to figure this one out. So we'll calculate the values of p for which the integral converges, okay? So I do the integration, and here's an important thing. It's going to depend on the value of p, of course. But it's only really going to matter whether p is equal to minus 1. Because if p is equal to minus 1, I'm going to be getting 1 over x, right? And that is the natural logarithm. In all the other cases, I'm going to be getting my old formula for integrating powers. Let's first do the logarithm one. This is what I'm going to get when I integrate, right? And the limit as natural logarithm goes of b as b goes to infinity is going to be infinity. So these series diverge. This one here, well, this is what I'm going to be getting, right? This is just my good old power formula. Now, again, I do my limit here. I'm going to put a b. And what happens here? Well, okay, this is not that straightforward to see. Let's think about it. And the thing you have to realize is that if p is a big number, right, like 2, okay, 2 is not very big, 1,000. It doesn't really matter. If it's positive, well, I put infinity here. Infinity to the power of 2, to the power of 3, to the power of 10,000. It's infinity. It's a massive number. It doesn't matter whether I'm divided by 3 or by 1,001. So that in all of those cases, it's going to diverge. When is it not going to diverge? Well, it's not going to diverge if the b ends up in the denominator, right? And to have it in the denominator, I need b plus 1 to be negative, right? I need b plus 1 to be negative, and then the b is going to go in the denominator. So that's the conclusion. Any series of this form, right, will converge if p is smaller than minus 1. And that's what you should know about p-series. An important thing to realize is that this one here, what is minus 1, I end up with 1 over k that diverges. Keep that in mind. Very important. Thank you for watching and goodbye.